And also, like for me, a privilege to really be able to catch up with the work which is going on, the great work which is going on with my old friends, colleagues, and supervisors. So, to start with, thanks so much for the organization and the invite. So before I get into the content, I really want to say a few words about Al. Like Jess and Stuart, I first met Al when we were doing our undergraduate solid state physics course at Imperial College London in 2009. And I guess unlike them, I've since left academia, moved into more the business side of industry. So I don't get to use maybe the practical teachings on a day-to-day basis. That being said, I have a huge number of fond memories of that time. For a few to think of is, Al dressing up as Santa in the last lecture before we broke for the winter holidays. Him bringing his PhD students in to play bass guitar connected to an oscilloscope to teach us about block waves, which actually might have been Stuart Higgins actually. And finally, just his passion and enthusiasm for the subject. Al would get so excited about what he was talking about. He would literally jump around the lecture theatre, which was really inspirational and great to see. Following that, Al gave me my first opportunity to work in a research group. I did my sort of final year undergraduate project with Al, looking at dielectrics for transistors. And subsequently, this work, co-supervised by Al, primarily supervised by Joachim Stanke, who's also unfortunately not with us here today. So I think there's somebody talking, and not on mute. I think I think it's a common theme of the talks today about the passion Al had for the subject, his real excitement for it. And I'm a sort of forever thankful for him giving me the opportunity to sort of begin in this field and get great enjoyment out of it, at least for the time that I worked in it. So it's a great thanks for that. So I'm going to speak today. I was also at the end going to speak a little bit about the work of we were doing at Johnson Matthey. We're interested areas. We're looking at Johnson Matthey. I think in the interest of time, I won't speak about that today. But if anybody's interested in learning more about areas of potential collaboration or areas you may be interested in moving into, please do reach out, and I'm very happy to have a conversation there. So this is a piece of work that we did as part of my MRes thesis, which was around actually 10 years ago, which is very, very difficult to believe. And the motivation, if I can get the slides, is that we all know organic semiconductors, we can engineer them in many ways. In one way, we can engineer them, for example, solubilizing side chains, and therefore the ability to deposit these from solution. And in the new name of the Center for Processable Electronics, this opens lower cost fabrication routes than traditional lithography. But as we know, to achieve high performance transistors, you need to have very, very high resolutions. And that's with Moore's law, transistors getting smaller, performance increasing over time. With liquids, this is often very, very difficult because when you go below the capillary length of a liquid, liquids tend to spread on surfaces. And therefore, it's very, very difficult to work with liquids on very, very small scales. Now, in the field, it's primarily inkjet printing, which is used to fabrication, printed fabrication in the submicron regime, partly because it's very easy to control, or not easy to control, but you can have well-controlled droplets. And therefore, this is really the area that has really taken prominence in submicron printing. But one of the drawbacks of inkjet printing is it's actually much lower throughput, I should say throughput, than contact printing techniques. So think, the inkjet printer in your house versus like newspaper printing. So what we want to do was investigate the possibility of using gravure printing to pattern features, not necessarily at this point electronics, on the submicron regime. And so this is actually the oldest picture I managed to find on my computer was of Al, and this is the old Polaric team, and I think you'll recognize one of the other esteemed speakers here today. This piece of work was carried out as part of the Polaric project, which was a larger piece of work that Al was running on printed electronics, and this is one small work stream of that. But, you know, in terms of acknowledgements, you know, obviously Al himself, Stuart, Nick, and Ben in particular on this project, as well as the Centre for Plastic Electronics. So, you know, if we sort of generalize contact printing into sort of 3 steps, no matter what way you want to go, there's sort of 3 key things you need to do to be able to have a contact printing process. The first is, you know, fabricating the printing plate, and you have to select what way you fabricate it based on, do you want the ink to be on the surface, or do you want on the raised areas, or do you want the ink to sit in the recesses? Something obviously you think about first. The second point is you want to selectively ink the printing plate so that, you know, you're getting a particular pattern. And thirdly, you need to take that selective inking and transfer it onto the substrate that you want. And so pretty much no matter what sort of contact printing process you want to go through, you have to go through these 3 stages. And if you look at gravure printing in particular, you know, so just to give a brief overview of how this works, you typically have a patterned drum with the features etched into it, which you want to transfer. The drum rotates, picks up the ink, which is covering both the surface and the grooves, which is the pattern you want to transfer. And what's called a doctor blade removes the ink from the surface, leaving it in the recesses. This is then transferred to a substrate and subsequently moves away and dries, and the ink rolls back. Sorry, the printing plate rolls back into the bath of ink. Now, for the purposes of what we were doing, you know, as part of this sort of, you know, 9-month master's thesis, we used a flat printing plate rather than a rolled one, and actually a rollable substrate, just for ease of processing. So, you know, I'm just going to run through these sort of 3 key steps that you need to go through, and at each step there was actually a key challenge and solution we needed to overcome. So, you know, in fabricating the printing plate to start with, you know, the first thing in a lab you would usually reach for to fabricate something like this would be PDMS. Problem with PDMS is it often deforms, especially on the sort of nano scale, and as well, it actually swells in the presence of organic substrates, solvents, so it's not actually really suitable for micron printing, submicron printing processes where you want to press a substrate against a printing plate. And so the first sort of challenge we overcame was we actually used a photocurable organically modified silica, which is also called Ormosol, or Ormostamp, which was the proprietary material we use. And effectively, we came up with a very repeatable process of fabricating features in the Ormosol down to, you know, on the order of, you know, hundreds of nanometers here. I think, you know, I think the smallest features we were patterning at this stage was about 100 nanometers. And this was a very repeatable process. And the Ormosol actually had the surface toughness required to actually be, you know, used over and over again and didn't swell in organic solvents. The second, and this is actually where, you know, a lot of the, I guess, science occurred as part of this process, was actually how do we selectively ink the printing plate? Because what we discovered very early on was doctor blading is not effective on the micron scale, and this is partially because of the fact that, you know, if you look at the, you know, incongruities on the doctor blade, that's on the same sort of like length scale as the features you're trying to print, and therefore what actually happens is you just end up with so much residue around your features. It's very, very difficult to actually, you know, selectively fill them and print them. So we needed to come up with a more elegant solution. That elegant solution that we found was called selective de-wetting. And effectively, you know, if you're able to tune your surface energy of your plate correctly using particular self-assembled monolayers, you can actually get to your regime where the contact line of your ink recedes across the surface, but then actually pins at these contact lines here, because the receding contact angle of the liquid isn't actually reached within the pit, and therefore what you're going to end up with is pits which are full of liquid and surfaces which are completely dry. And so, you know, if you would look at it theoretically, how this would actually work from a contact printing perspective, it's actually you would have no doctor blade, and the pits would sort of naturally fill with the liquid through this selective de-wetting. And we found this was actually an extremely repeatable process, and actually very, very, very successful across a very wide range of length scales. You can see here, so this is sort of the empty pits and this is the filled pits. And you can see even for long lines, diamonds and circles ranging down to one micrometer, it's actually a very, very effective process to fill pits. And the process here was simply when you got your surface energy of your printing plate correct, you can literally deposit the solution that you want to fill the pits with, spin coat the remainder off, and you're left with a very, very highly effective method of selectively filling the pits. So now that we have that, we then need to print the, apologies. We then need to print it. Now, the third issue that we ran into was when you're looking at features which are sort of less than a micrometer in size, even very high boiling point organic solvents like trichlorobenzene evaporate almost immediately. And therefore, when we're trying to actually deposit, say, organic semiconductors from it, it's actually very difficult to fill the pits and then actually deposit the semiconductor. Now, this is sort of a tactical issue. If you were to design the process correctly, I'm sure this wouldn't be an issue, but for the purposes of demonstration, we wanted to use a curable pre-polymer. So effectively something which doesn't evaporate, but we could actually cure. And so what we were aiming to do in the time was actually print effectively a transistor structure using this method. And so, for example, here is the printing plate with I believe it's a 0.5 micron wide channel, which we're able to effectively transfer onto a gold substrate and subsequently use that as an etch resist. And by using back illumination, we're able to create sort of transistor structures with less than, I guess a micrometer in source drain distance. Now, so I'm actually going to stop there in the interest of time to get everybody off on their weekends. But again, in summary, fabricating the printing plate using a photocurable organically modified silica, using selective de-wetting as a method to very repeatably selectively fill pits, and been able to print features on the sub-micrometer scale was achieved through this. And I'd really like to thank the organizers and thank Al for the help with this work and being an inspiration. So thank you very much.
Thanks so much, David, for that. And that was a really, really interesting talk. And